Hello world, it's Siraj, and I've built an app called Dharma Security that I'm going to demo for you. This is a cybersecurity app. Check this out. So the way it works is basically it's an analytics service, and what a customer does is they will embed a little bit of JavaScript into their checkout page, and this is going to allow them to automatically detect whether any transaction is fraudulent or valid. And so what they can do is they can log into the dashboard. Let me log in. And it's going to show them a bunch of accounts, and some of them are going to automatically be removed. I can search for different accounts, like how about Jude, or how about, what's up? And most of these accounts will be removed automatically, but some of them will be in real time. It's going to analyze them and then eventually detect them as real or fraudulent transactions, okay? And there's a bunch of graphs here I've built as well that shows how many fraud accounts have been created, how many have been destroyed, which ones are relevant, all these different graphs. But there's so much in this video that I want to show you today, and there are 3 key learning objectives for this video. The first one is how to build a scalable analytics service. The second one is federated learning. And the third one is secure multi-party computation. I cannot wait for you to watch this video, so here we go. These days, many companies are using machine learning pipelines to automatically detect fraudulent transactions instead of hiring a team of humans to do so. These models are using hundreds, if not thousands, of different data points to accurately classify a transaction as valid or fraudulent. But it turns out that even the most sophisticated methods are unable to correctly identify a lot of fraudulent transactions. And the reason for that is because of the change in fraud behavior over time. Often, the past data on which these models are built aren't effectively predicting current frauds, since fraud behavior changes in real time. What was considered fraudulent behavior many months ago might now have an entirely different meaning. That means that if we want to build a robust pipeline, we need to build a model that is continually learning, one that's continually updating its predictive capability using current data about a user as they make purchases. We're going to need to be feeding our model user data as it's generated in real time as a stream of data and have it learn from it. As the number of users we're tracking grows, so will the amount of data that's going to be streamed. So in order to do this well, we're going to need a set of tools that will allow us to build a scalable application. Let's talk about them. We're going to need to host our app somewhere so that our customers can access their dashboards via a web browser to monitor fraudulent activity. AWS, Google Cloud, and Microsoft Azure are all industry standard cloud hosting options, and each has a suite of tools that we can use to add functionality to our applications. But in this tutorial, I'll be using AWS because I'm just generally digging Amazon's vibe lately. They're doing a lot for developer education in 2019. We'll want to build a pipeline that enables us to have 2 components. We have our app that's hosted on AWS. This is where our customers can see their analytics dashboard. But we also have a client-side component that they'll have to implement themselves into their own apps. There's a JavaScript snippet that they'll need to embed into the checkout page of their website. This JavaScript snippet will send a data stream to our AWS app containing user metadata like the time they spent on the page, their IP address, and the web browser they're using automatically. If you've ever used Google Analytics before, you're aware of this practice. They have their customers do the same thing. They'll also need to implement an API call to our AWS app as well that contains sensitive card information whenever a purchase is made. Our app then concatenates both the secure transaction data and the user's metadata as input to a machine learning model, which will then output a score that says how likely a transaction is fraudulent. It will return this result as a JSON response to our customer's app, which they can then use to prevent a transaction that is very likely fraudulent. It will also notify them via their analytics dashboard. Sounds simple enough, right? Yes, but now I'm going to backtrack a bit. This architecture would have been great for 2018, but the world is changing fast. Privacy laws are being enacted globally across many different nation states. Europe's GDPR is probably the most famous example of this, requiring companies to keep user data private unless they specifically consent to sharing it. So allow me to explain how we'd slightly modify this architecture to preserve user privacy and still learn from their data. Our little JavaScript snippet for sending user metadata will actually encrypt it first, then perform some client-side machine learning from it. Then what we will actually send to the server is not their raw data, but what it's learned from their data in the form of an encrypted weights file. This way, we as a provider aren't using any sensitive information, and thus our app is compliant with privacy laws globally. It also makes it easier for us to get new customers because it'll make it easier for them to trust us. So that's how the architecture works at a high level. Now let's get into the details of what AWS tools we'll need to use to build this. There are 4 of them: Lambda, Kinesis, S3, and Athena. When a user is checking out, a request to our API is initiated. Then our AWS app will pass that event request to Lambda. Lambda is an event-driven computing platform. It runs when triggered by an event and executes code that's been loaded into the system. For example, a simple use case would be that every time an image is uploaded into Amazon's Simple Storage Service, or S3, a Lambda function could automatically resize the image. The reason to use Lambda here is because it allows us to only pay AWS when functions are executed, instead of just general server hosting costs. We only pay when user event data is processed and written to a suitable data stream format known as Kinesis. Kinesis is a tool that's capable of processing hundreds of terabytes of data per hour, things like operating logs, social media feeds, and in our case, financial transactions. As we scale, all of these real-time transactions could create a potentially huge queue, which could cause our app to slow down. But Kinesis helps us avoid this by creating a scalable data stream. We'll then use its Firehose functionality to write the file to S3, the Amazon Cloud Storage database. Then we'll query that S3 database using Athena, a query service, so that we can immediately display it in the analytics dashboard. So that's an overview of the pipeline. Let's now set up this pipeline ourselves programmatically. Come on, I'll walk you through each step. All right, so let's build this analytics app basic structure. How do we do this, right? So I found this great tutorial on the web called Building Open Source Google Analytics from Scratch that I'm going to complete in this video with you so you can see how it works, and then we're going to keep building off of that. But the basic idea is that we want 2 components. We want the dashboard, right? So the customer can log into the dashboard, see the analytics, but we also want this JavaScript snippet that we can give to them. They'll embed it into their checkout page, and it's going to automatically allow them to detect, whether or not this transaction is fraudulent or real. So let's go through this tutorial together. There's a lot of AWS tools that this tutorial talks about. Let's start off with the first step, which is installing serverless globally. So first of all, serverless is a service that is basically the idea of serverless. Really, there are servers involved. What it means is that you can scale without having to think about servers. It just kind of automatically scales as your app grows in size with more users and more data streams, things like that. As your app gets bigger, you don't have to worry about buying more servers or calling up Amazon or Google Cloud like, hey, I need another server. It just automatically happens. So the name is kind of confusing, serverless. There are servers involved. You just don't have to worry about the servers and adding servers. All right. So I wanted to make that clear. And this is a service that lets us build these serverless applications pretty fast. So let's start off with this. Let's go through these steps together, and I'll show you what the output looks like. All right. So the first step for us is going to be to install serverless globally using npm. So I'll say npm install serverless globally. And then it's going to say error, permission denied, of course, because I've got to do sudo. I got to be root. I got to be the G over here. And once we do that, I'm going to fetch a bunch of metadata. Great. So serverless was installed. Now I can say serverless login. And so I'm going to be able to log into this serverless web app automatically. It's going to open up a browser. It's going to say, hey, how's it going? I'll log in. It lets us deploy and manage a serverless architecture really easily. And okay, great. Let me add a new application. Let me see what it says here. My new app test, and add that application. Great, I've got this new app. It's called app test. Now let's go back to this. Now we're going to create an event collection service from a node.js template. Basically, this tutorial is all about collecting a single event, like a page view, and that's it. But we want to collect a bunch of different data, right? We want to collect all that user metadata. We'll just add that into this app later, but let's just start with like this simple event collection service from a node.js service. So we're going to create this node.js app, basically. That's what it is. And so this command will let us create that automatically. We've done that. We want to add the AWS SDK so we can access all these AWS features. Done that. Now we're going to install this Yarn package manager. Oh, I already have Yarn. Okay, so basically, let's look at what this gave us. So we now have this. Oh, I'm in a different directory. So let me just make another directory. Make directory Amazon test, cd Amazon test. All right, I'm here. And let me just do the same thing again. Let me create that same little kind of scaffolding bare bones app again. Okay, and now I should have it. There it is. So let's open it up. Let's look at what it looks like. We've got a handler.js, and then we have our serverless.yml file, which is a bunch of configuration options. And so it says you need to update your handler.js with this snippet that's going to collect the event. What this does is it collects page view events. That's it. So that's the event that we're collecting. And so this code snippet right here is going to allow us to do that very simply. We'll paste that in. And it's going to create a Lambda function that will collect that page view event. And so this is the JS snippet that we're going to give it to a user, and it's going to be like this. They're going to embed it like script, our AWS app .com/handler.js or whatever we want to name it, like that, and then script. And so they'll embed this JS script from the web on our website, and it's going to fire a Lambda function whenever there's a page view. That's it. But we're going to modify this later to add more events to it, all right? So that's the basic idea. And so this is the Lambda function right here. So we've got kinesis, and then what kinesis does is it says, puts a record, you got to put record here. You get to await it, collect asynchronously. So it's, here we go, we're adding in all this. Here's where we're adding the page view data, and we send it to this event collection stream on our AWS app, all right? So that's that. Now we've got to modify serverless.yml. So we'll go back to serverless.yml to contain all of those. We need to delete all this stuff, just like that, like that. And that's going to assign an API gateway event to trigger it. And now we can deploy this to AWS. Let's say deploy to AWS. AWS credentials not found. Of course, we didn't link up our serverless app with AWS. So let's go back. Let's see what it looks like. We've got to create an IAM user and access key, and then we'll do that. So let's go through this together. Okay, and then once we create that access key and the secret access, then we hit deploy and we export them as these global environment variables. So I will log into AWS. I'll add a user, test user, programmatic access. They get administrator access, create the group, review, create user. All right, so here's the access key ID and the secret key. So what I'm going to do is I'm going to export those keys. Let's go back to the tutorial. And where was it? Here we go. So I'm going to export my access ID key here. Here's my access ID key. Where was that? I'm like pasting it into the URL bar. Okay. So export that here. Okay, that's my access ID key. And then I want my secret access key. And I'll take that. I'm going to delete this, so no worries, before this video is released. And put that there, and then I'm going to put it there, and now I'll hit serverless deploy. There we go. Yeah, connected to AWS. It's connected. That's the connection I needed. All right, let's keep going. It's being all serverless over here. Good, deploy it. Thank you. Thank you. All right, Look at that. Look at my little post endpoint over here. Look at me making little post endpoints. All right, let's test this endpoint, curl to it. So I'll say here's my endpoint, made this post endpoint. If all is well, it should say this. That's exactly what it said. That's exactly what it said. Thank you. Now we're going to set up Kinesis. Here we go. So let me say services, Kinesis. Okay. I'm going to create a new data stream. Siraj's stream. Let's just say one shard for now. I don't know. Just to like start. Create the stream. Create a delivery stream. That's what I need to do. Delivery stream. And the source is a Kinesis stream, which I just made. And then we're going to say, what does it say? Disabled, disabled both. Great. Disabled. Destination, S3, the bucket. Got to take it to my S3 bucket I made a while ago. And then next. Next. Oh. Fine. Yeah, this one. I just made it. Go back. Thank you. Next. Create. Now I'll do the same with this. Remove this part. Good. All right, so now we're going to set up AWS Athena for querying those analytics. So we're going to first navigate to Glue, and in Glue, we're going to select databases, add a new database, call it AWS Web Analytics, create an add crawler, name it events caller. Okay, so we'll add it, let's see, databases, add database, call it AWS Web Database, done that, then go to crawlers, so add crawler, have a crawler name, and here's my crawler right here, which I did. And so choose the S3 bucket as the data store, added the role, database, great. Now go to Athena. All right, so I'm just kind of like blowing through this, but I just want to show you guys that like this is doable. That's basically the point of this. Like this stuff is doable. And okay, and so Athena will query the database that I've already created right here. So I just type in, you know, one of these queries to make it work, select from. That's going to allow us to query the database to get those events, etc. And then we are going to create this cube.js account, which will allow us to, it's this open source analytics framework, cube.js. I found it's pretty cool. And so we'll create the account, we connect it to SQL, and then we can see the analytics in the dashboard. And then we want to create a React Analytics dashboard. So basically what we just did was we created that functionality that the user can then insert that JavaScript into their website and then access the dashboard. But we have to create the dashboard now. So we'll say yarn create React app dashboard, which yarn is like NPM. We'll then cd into the directory, add all those dependencies that are necessary, and then create this track.js file pointing to that endpoint that we just created. So this dashboard is going to pull the data from the endpoint that was tracked and put it into this analytics dashboard, and then we can display it on the screen. So that's it really. There are just two files here. We have app.js, and then we have track.js. And once we do that, we have our dashboard. There we go, happy hacking. Let's keep doing all these little dependencies that we have to do. Done that, okay. Now create a track.js file in the analytics dashboard, paste this in, okay. cd analytics dashboard, nano track.js, paste it in, yes. And then go to app.js, add in the snippet, or replace app.js. There it is. Replace, boom. No, okay. Replace the API key, which I'll do, and then you'll see the dashboard with 2 charts. And then we can deploy it to an S3 bucket. So this whole tutorial, check it out. It's gonna let you build this analytics dashboard super fast. I just wanted to show you what the outputs look like, kind of what the AWS setup process looked like. But moving on, we have some other things to cover. This was just the beginning.
Hey Siraj, can you put God picture on my phone? Put God picture.
Sure, Grandpa. I'll just write a Lambda function to do it asynchronously from the web.
What the hell?
All right, so that was the AWS pipeline, the scalable analytics application part. Now we want to do some machine learning. So let's see how we do this for machine learning. So in the app, it asks us to make a React framework, which is a JavaScript-based framework. But I found that Python-based web frameworks are just better for machine learning. Like, you don't have to deal with as many dependency issues. Like, things just integrate better. In the end, we're going to start using PySift for secure federated machine learning, which is quite a mouthful, but it just know that it makes it easier to use Python. So we're going to switch that backend to a Flask Python web app backend. And what I did was I found this great GitHub repository that does just that. It's a Flask web app that basically performs fraud detection for credit card transactions. And so we can basically run this on our machine and then add the same functionality we added in React, but this time in Python. So let's open this up and see what it looks like. cd into that. All right, so what do? We say pip install. I already got Flask. Say python.api, python api.py, python 3. Got to install those dependencies. I think it's just good for me to show this stuff. It's not as exciting, but like, let's just show this stuff. Sudo pip3 install pandas. You got to install these dependencies for things to work. Where's the requirements? Address is already in use. Yeah, I understand. Let me close that address in use. Let's try it again. Good. It's working. Awesome. We got it running locally. Fraud detection API for detecting credit card fraud. Great. And let's see what it looks like. So what's happened here? Okay, so here's the endpoint, the API for endpoint. It takes whatever a transaction's format is, it loads this model, it performs inference and it returns the result. And here's the result, right? So here's really the predict new transaction bit. This is what matters to us right here, this predict new transaction bit. So how did they train this? They use a logistic regression model on Kaggle data. I think it's Kaggle data. Yeah, data sets from Kaggle. Let's take a look at this. Credit card transactions as fraudulent or genuine. And so Kaggle has this great fraud detection data set. There are more data sets out there, but this is a good one where the label is fraudulent or not fraudulent. And that's this data set right here, time, V1, V2. Okay, so they reduce the dimensionality of all these features, so we don't know what exactly they are, but we're gonna do the same with our own user metadata. We're gonna reduce the dimensionality, use PCA or one of these dimensionality reduction techniques to then make it easier for a model to interpret what's happening and to anonymize the data as well. It's also a security feature. And that's gonna give us that. So by the way, so basically logistic regression, I've got a great video on this. It's one of those things where like, I've made two, so check out Math of Intelligence Week 2 and this binary logistic regression tutorial video. Basically, you give it some labeled data and it's gonna be a great classifier, outputting probabilities of how likely something is to be fraud or not, or whatever the use case is, spam, not spam. So that's the use case. So really, I think the value I can provide you, rather than explaining how logistic regression works again, is to say that we need to get more data sets, more fraud detection data sets, more than just the Kaggle data set, right? Because we're going to be building a data set in real time because we wanted to perform real-time machine learning. But Kaggle's got a great data set. Data.world looks like it's got some great data sets as well on fraud detection. There we go. So we want to concatenate all these data sets, and that's going to take a while, but we want to get more data to make our model better. And I also found this great blog post on real-time learning for credit card fraud detection. Basically, this guy uses this library called ArtML to do this. I thought this was really inspiring to see how they also use PCA using the same Kaggle data set. They got some great features, but basically they were saying the same thing, that fraud behavior changes in real time, so we need some kind of adaptive real-time learning for credit card fraud detection. What we could do is we could take this locally running Flask file and we could implement ArtML as well to do that, to have this like continuously learning model. And so the Kinesis data stream is going to send all those features to our app. We're going to be performing that real-time fraud detection learning from it. And so our weights are going to be constantly updated over time. So the actual learning process is going to be different though, because right now I'm talking about a server client model, right? Where you have one machine learning model in the cloud, and then you've got your server, which is like some mobile app or a website or whatever. But what we want to do is we want to perform federated learning and secure multi-party computation to preserve user privacy. I know you don't know what those words mean yet, but let's now talk about them. Our app currently uses a basic server client model. The model is hosted on our AWS server, and the client sends that user data to our server for training. But what if we could perform training client side instead of server side? This is called federated learning, and this term was first used by Google in a paper published in 2016. The main idea is that instead of bringing the data to the model, we send the model to where the data is located. As the data is located on several devices, the model is sent to each device and then sent back to the central server. One simple example of federated learning in the real world happens with Apple devices. The application QuickType, Apple's text prediction tool, actually uses models that are sent from time to time to iOS devices via Wi-Fi, are trained locally with user data, and then are sent back to Apple's central server with their weights updated. Let's be more specific about how this works. In a series of rounds of communication, the server selects a number of random clients to participate in training. Each selected client downloads the current model from the server and performs some number of local updates using its local training data. For example, it may perform a single epoch of optimization, then the client uploads their model update. That means the difference between the final parameters after training and the original parameters. And the server averages the contributions before accumulating them into the global model. So that's federated learning. Let's now talk about how to add some security to this process via secure multi-party computation. It's a cryptographic technique that lets multiple parties jointly compute some function while keeping their inputs private. The primitive that powers MPC is the ability to split a piece of data into multiple encoded parts known as secret shares. On their own, the shares reveal nothing about the original data. However, if two parties perform the same operation on a set of shares and then recombine them, it's as if that operation was performed on the original data. There are two common mathematical primitives needed in deep learning: addition and multiplication. While addition and multiplication seem trivial, you can use them to construct convolutions, pooling, dense layers. We can even create various activation layers using approximations. Basically, all the standard operations a neural network performs. Let's look at how this works mathematically. We'll have two parties that will be performing computation. Let's say there's some number we want to perform computation on. What we do is split the number into two values. For example, a 5 could be split into a 3 and a 2, or an 8 into a -1 and 9, since these pairs add up to the original number. We generate a cryptographically secure random number, then subtract what we're trying to share. Each party will exchange half of their shares with the other. Then they will operate on their shares and exchange their results before finally recombining their shares into a final answer. Addition is the simplest operation we can perform with secret shares. Each party adds their shares, then exchanges the results. They're both assisting in computation without ever knowing what the original number was. In the context of secure private deep learning, we can combine the power of secure multi-party computation with federated learning to get some amazing results. Luckily for us, all of this is neatly packaged into the PySift library from the OpenMind organization. I'll demo how it works programmatically. Let's look into this together. Hey Jude, let's do some math. Take a number and make it better. Remember to split it into two parts. Then you can start to make it better. All right, so welcome back to the coding portion. So we just talked about OpenMind. Let's look at what OpenMind looks like. So OpenMind is this great organization run by my friend Andrew Trask, and in this repository is everything we need for privacy-preserving, secure deep learning. It's got federated learning built in, it's got secure multi-party computation built in, and it's got differential privacy built in as well, which I didn't talk about and I won't talk about in this video because to me, that's just a little too much, even after doing everything. That's just too much to fit into this video. We're experimenting here. I'm experimenting to see how I can increase the value of these videos without over-saturating you with information, right? So I want to show you the bits that are the most important. So this library called PySift, oh look, they got a little shout out to me. Thanks guys. So this library is called PySift. And PySift is going to allow us to perform federated secure deep learning in the cloud. So what we're going to do is we're going to replace scikit-learn with PySift. Okay, so that's going to be on our server. And we can go to the examples, tutorials, federated learning with secure aggregation, another word for secure multi-party computation. And look, they built a simple PyTorch model. We can build in whatever we want, simple neural network, and then they hook it. So here's where the Sift part, here's where the PySift OpenMind part comes in. We can define multiple workers, these are clients, to be computing parts of our machine learning model. So we'll define them in Python, we'll send the data to those workers, we'll train it, we'll test it, just like that. So this is something we can incorporate into our app. Now in terms of adding this encrypted aggregation, there's quite a lot here, but I basically wanted to point you in the direction of how to do this and putting it all together. But I also wanted to say one more thing. So remember that there is this client-side JavaScript snippet, right? So they'll log into our analytics dashboard, but then they also have this little JavaScript snippet that right now, all it does is it sends some event data, right, to our server. But what if we want to perform federated learning and have learning happen client-side as well? Well, inside of that JavaScript snippet, we're going to add a little bit of pysift.js. So let's look at what I mean by that. Pysift.js is a client library for OpenMind. Sorry, it's called sift.js. And basically, we just embed this script tag into our own JavaScript file and then give them like this wrapper JavaScript. And it's going to allow us to define those workers locally on their machines or wherever their website is hosted. And then send all that data, the learning data, the learned data to our server. So in guide, okay, so let me just like type out some of this stuff just to like JavaScript, right? So we'll create a new sift object, var sift equals new sift URL, and then this is the URL of our endpoints, our dev collect. Remember that endpoint we had? And then sift.start, and then we'll add tensors, sift.add tensor, add tensor, add tensor for as many for as many user features, those metadata points as we have, right? So the IP address, the web browser, all those things. And then we're gonna run an operation locally, add it as a promise. These are just event listeners. And then we send the data to the server. So yeah, so that's kind of like the basic idea. There's a lot of moving parts here, as you can see, and this app is not finished, but really the point of this was for me to try to bring you the most value by taking something that is relatively secret. Like, you won't find tutorials on fraud detection online. It's because it involves security, it involves sensitive information. You won't find complete tutorials on how to build a fraud detection analytics app on the web, because it kind of goes against people's interests. People want to make money with these. Like, why would they show you? But I'm showing you because I'm a teacher, and that's what I love to do the most. So this app is not finished, okay? It's not finished, and I know I kind of rambled in different directions here, but really my point was to show you the different directions of how to put these tools together so that you can build a secure analytics app that is made for cybersecurity. There are 3 things to remember from this video. If we easily want to create a massively scalable application, we can use different components from services like AWS, Google Cloud, or Azure to do so. Federated Learning allows us to send a machine learning model to a user's device to train on locally, and then send the results back to the global model on a server. And secure multi-party computation is a cryptographic technique that lets multiple parties jointly compute some function while keeping their inputs private, allowing for privacy-preserving machine learning. The winner of my last coding challenge is Omar Kusma Fair. Omar used the Ramanujan machine to automatically generate a conjecture for pi. I really like how he built plots for visualizing the process. Amazing work, Omar. If you like this video, please share it with your friends, and until next time, wizards.